But my team at Verizon, we have a pretty simple mission. It's speed up the adoption of new technology in our network to make the network run better. And when you look across all the different technologies that we're looking at right now, AI is one of those things that's in the hot seat that everybody's excited about and that we're spending a lot of time on. For us, AI is simply a means to an end, and you'll kind of see that as we go through the slides. But it's a pretty powerful tool and a pretty key means to that end for us. So to start off, I have to ask a question before I get to the title of the slide is, for those of you who are not familiar with AI or you're getting into it, the first thing you need to know about AI is it's all about cat pictures. Any kind of AI thing you do or class you take, it all revolves around cat pictures. So I had to have a cat picture in my AI talk. And obviously there the pattern is there's a bunch of cats. The kind of interesting thing is your eyes see that there's cats in the pictures, your brain knows it's there, but if I asked you to write down a list of rules that you could apply to any different picture that could tell if there's a cat, you would be really hard pressed to write down that set of rules, right? You might start with, well, look for pointy ears, right? But that one up in the top center, there's no ears on it. You might say, well, look at a particular shape, but we got different shapes all over the place. So that this is one of those things where if you're at home at night and having trouble sleep, like ponder the fact that you can see it, you know it's there, but you can't write down why you know it's there. And for me, this is a really good illustration of the power of AI, right? It can look at this data, these different data types, and in places where you know something's there and you can't write down a rule, AI can come up with a rule that finds those things. Or in cases where you just look at a mess of data and you don't know what's there, AI can extract patterns for you. And so in cases like computer vision, in cases like speech recognition, AI has proved really powerful because it can do those things. If I go to network data, it's kind of a different story, right? If I gave you, this is a Wireshark, dump on the right and a configuration file on the left. If I gave you a pile of Wireshark traces, like, what's the equivalent of, oh, there's a bunch of cats? Like, we don't know, right? And maybe if you have a super specialized part of the network, yeah, you can find that, but the average person on the street doesn't know. And we don't know if there's patterns there. We don't know, I have cats, I have dogs, I have birds, I have fish. Like, we don't know those things in the network world, which is one of the reasons why applying these cutting edge AI techniques to network problems has been so difficult. So what I'm going to talk about next, setting the stage with AI and what it can do, is a couple of things that we've put in place at Verizon to help us go down this path, and then also talk a little bit, depending on time, about use cases that we're currently looking at. So the first thing we've done in terms of making AI real and having success at applying it is thought really hard about what are the ingredients? What do I need to actually make this successful? And I have 5 things up there. What's kind of interesting is I have a mix of things that are commodity, things that are not, things that are very specialized to our particular use cases, things that are not. And for those of you who are curious, one of the reasons why AI became so powerful within the last 10 years is because some of those things weren't available even in the early to mid 2000s, right? Really in the early to mid 2000s when AI exploded or got so much popularity, it was because that the compute, we all of a sudden got GPUs, so we had lots of compute, it was very cheap. There were some algorithmic improvements that were largely put out in open source, but that helped a bunch, and then data was the big key, right? Once everybody had cell phones, and the internet, I have lots of data that can be out there analyzed. But that's not all I need, right? And from a Verizon perspective, one of the things that we've emphasized and really hammered on is that if you're going to do this correctly, you need that domain expert piece up on the top. Like, everybody focuses on the data scientists, but if you don't have somebody who understands the problems you're looking at, you are going to fail miserably, right? So if you are looking at a radio access network problem with eNode Bs and BBUs and all that kind of stuff, if you just have a bunch of smart data scientists, great compute, great algorithms, a ton of data, but nobody who knows those systems, you're going to fail. And so what we've been doing at Verizon is trying to pull together all of these particular use cases or all these ingredients for the use cases we have. Just one more kind of process thing as we've been trying to execute these projects is that a lot of people get really excited about building the algorithm and creating the latest neural network and all of that. What we've tried to emphasize is that it's really only one piece of making this operational, right? If I look at a sort of an end-to-end flow for making something operational in the network, I actually need 3 steps. Data science, that algorithm, building cool neural networks is just one of them, and quite frankly, it's the easiest. On either side of that building the algorithm, I need at the beginning a bunch of what we call data engineering, which is getting the data, making it accessible, making it usable, cleaning it up. And what you'll see typically is that's 80% of the problem, at least. On the other end, once I have this cool neural network that I've trained, it does nobody any good if it's living in Python on my laptop. I need some way to transition that into an operational system where it actually gets used and benefits the business. And again, this is a pretty tricky area too, because depending on the environment you're going to deploy into, the performance requirements, the language requirements, the memory requirements, all of that varies. And it's not just as simple as, hey, I wrote a Python, so a Python script, and now let's go put it in production. So we've spent a lot of time on getting this pipeline put into place so we can look at things from end to end and actually go from good idea on the use case to something that's implemented operationally. Now, if you look at, so that's kind of the process piece, right? And that's not the sexy piece, but what we found internally and when we're talking with people that are either coming to us with solutions or as we're developing use cases ourselves, that's where things fall down. So I always talk about that in every time I give this message. But if I move to the more interesting pieces, let's talk about where we're using AI. And one thing we like to try to emphasize to people is that you have a whole spectrum of techniques and capabilities that AI can bring to the table. From the very basic stuff, which on the left, which we would notionally call analytics, to more sophisticated, deep learning stuff that you read about in the paper that Google or Facebook or any of the hyperscale companies are using. But for us, the ultimate level of sophistication is we want to move to apply all those things to get automation and extra performance in our network that's just not possible if only humans are doing it. So for us, these techniques, like I said, they're a mean to an end. And our end is we want to be able to automate things so that we can either do more or do things more quickly or eke out extra performance that are just not possible without these algorithms. To give you maybe more of a flavor of what we're actually working on and things that are in flight for us, I can start at the left. And so we have this thing in the network called a killer mobile. So if you're not familiar, sometimes software on phones gets bugs, and it actually causes your phone to misbehave and degrade network performance quite a bit. So one of the more basic things that we've done is say, hey, can I look at KPIs or metrics coming off of the network, and if I see a cell site that's having a problem, automatically detect that it was one of these killer mobiles causing the problem. That way, instead of the engineer having to chase down a bunch of, was it this, was it that, was it a misconfiguration, we can automatically tell them, hey, that site's issue, it's a killer mobile, go figure that out and fix that instead of wasting your time with other stuff. To show you sort of the evolution of that, I go now to the right, I should have put it on the top, but I go down to the bottom right, and now we've taken that to the next level and automated it. So we've identified, now that we know when a killer mobile is impacting performance, we've identified certain cases where we know how to remediate killer mobiles, right? It may be as simple as sending a reset command to the killer mobile. And so we took that to the next level and said, if I know that's the fix, I don't need a person to send that command. I can then take that basic analytic capability, incorporate it into some type of automation system, and then now, anytime there's a cell site with a problem that was caused by this type of killer mobile, I can automatically remediate it. If you look at some of the other things we're doing, I think there's probably some fairly obvious things. about, I have alarms in different parts of the network, and an alarm over here might cause an impact over here. And the guy looking at this doesn't have visibility into this. So how can we do some of that correlation to speed up troubleshooting, to speed up problem remediation? Again, the vision there is, can I then take that to an automated space? If I look at some of the more, at the next level of sophistication using what we might call traditional machine learning algorithms, we're doing some stuff there with, can I predict when a particular network element, specifically an eNode B in this case, has configuration issues? Again, this may seem like an easy problem, but when you look at the number of possible configuration parameters, the number of different ways it can be configured, if I'm having a performance issue on a cell site, it's not always obvious that it's a configuration issue causing the problem. And so we're here applying machine learning techniques to automatically identify those. If I go to the next level of sophistication, deep learning, we are actually actively doing some stuff there. I gave a talk about a month ago at NVIDIA's big conference talking about a particular use case there, and I'll run through some slides on that just to give you guys, again, more of a flavor on a use case. And then we're doing some stuff with RF planning. So as you can imagine, like coverage, performance, that kind of thing is really important for a company like Verizon. If you see all the commercials about we feel like we have the best network and that kind of thing, you can imagine how much time and effort we spend on that. And so again, here we're looking at how can we use deep learning to take what we're already doing and enhance it to the next level. But if I go specific now into a particular use case, and I look at Verizon's network, so on the left, a network like ours has tens of thousands of cell sites. Each of those cell sites has multiple beams of RF energy that it's radiating. We call those a carrier. Each site has multiple carriers. So in our network, I have hundreds of thousands of carriers. If I look at each carrier, I have specific performance metrics that we're looking at to determine the health and the performance of that carrier. So if I look at all of the metrics on all of the carriers on all of the cell sites in Verizon's networks, that is millions, if not tens of millions of metrics that I have that I'm trying to look at. And today, one of the really great things we do is sort of bring all those metrics together, do some analysis, and let people know after the fact to say, hey, based on these metrics, this site's having a problem. And so there's kind of a screenshot of one of the tools we use, and if I'm a network engineer monitoring the performance of my network, I go look at that site and it tells me, hey, these sites are having issues based on those performance metrics. The place where we want to get to, and that black line should be straight, whoops, is actually, instead of analyzing the metrics after the fact, being able to predict those metrics out in the future and be able to tell the network engineers, hey, this site doesn't have a problem today, but based on what I'm seeing, it looks like we're going to have a problem in the future. And so here we're expecting those machine learning algorithms and deep learning algorithms to look at the data, decipher patterns that can predict the problems in the future. That way, the network engineer can proactively intervene before the problem happens. Fairly obvious use case, I realize, but that kind of thing could be very powerful when it comes to a network. So how have we tackled this problem? And for us, it really happened in two phases. And one I'll call the traditional, which is on the left, and then sort of the more advanced, sophisticated on the right. In the traditional approach, we essentially looked at each KPI. For those of you in the data science world, each KPI is what you call a time series, so a metric over time. There are well-known, well-established algorithms to analyze time series and predict the future. I have some of them up there, ARIMA, moving average. Facebook actually released an open source tool called Profit that does some of this. And even on the deep learning side, we tried to use some things here. The key was, though, if I have tens of millions of KPIs, building tens of millions of models and then predicting the future is slow. And it also suffers from the fact that if I have cell sites in a particular geographic region, they're probably going to experience similar performance, right? So if a weather event goes through or it's Sunday, Saturday night in a particular area, the performance might be similar. In the same way, if I have cell sites at hospitals or schools, you might expect the weekly and diurnal patterns to be similar. And unfortunately, when I'm building separate models for each of these KPIs, I can't take advantage of those similarities or those correlations. So given the sort of time it takes and the inability to leverage these correlations, we took a completely different approach where we took all of those tens of millions of KPIs, fed them into one deep learning model, and basically challenged the deep learning model, are you smart enough to look at these tens of millions of KPIs and find the correlations between them to do better predictions? And what we found out, I think I took the results slide out of here, but what we found out was on a small subset of the KPIs, about 10,000 of them, in this traditional approach, it took 4 hours to train the models and predict the future. With this deep learning approach, it went from 4 hours down to 4 minutes. And we essentially saw a 0 increase on the time it took to do that prediction as we went from 1 KPI to 10,000. So when you look at scaling this across tens of millions of KPIs, the time it takes to do it is essentially flat, whereas in this traditional approach of a separate model is just increasing. So that was good. The second part that was good is on the deep learning piece, we actually saw increases in accuracy in the model. Sometimes I think it was almost up to 2 times better error rates, or 2 times less error rates on this deep learning model in terms of predicting the future. So for us, this was kind of an exciting thing because we had this sort of hypothesis that all the cat guys with computer vision are getting great performance with these deep learning models. What can we do on the network side to sort of see similar performances? And based on this particular example, it seems promising. So in summary, AI for networks is hard, but it's possible. For all of you who took pictures of the slides, remember those 5 key ingredients, remember the 3 key steps. And based on what we've seen, there's a number of use cases where this can be done and where we're seeing benefits. So with that, I will try to keep us ahead of time and see if there's any questions.
Yeah, that's great.
So for the AI stuff, is something you develop internally, or you have to rely to third parties software?
Great question. So what we're finding, if I go back to this slide, I'd say it's a mix of internal and external stuff. The challenge is when somebody comes to me with an external capability, my first question is, okay, what's the value add you're providing? Do you have an algorithm that's not available? To be honest, a lot of the cutting edge stuff that's out there today is available as open source. So that's a conversation we have. We also say if you have a trained model, what data did you train it on? Because if it's not similar to Verizon data, then its applicability may not be so great. So we're doing a mix of both in terms of downloading the open source algorithms, training it on our data, and then using it, but then also talking to vendors in cases where they might have an algorithm that's not commonly available or somehow they had access to data that we don't have at Verizon that we felt might be useful.
Trust those open source models?
Yeah.
Thank you very much.